you should secure your FPGAs and how we can help. Then we'll move on to ensuring your data is protected as we move into the quantum computing era. And we'll welcome our partner, Zyfira, to show how you can start on that transition today. So let's get started with what AI has to do with FPGA security. And first, I'll start with a pop quiz. So everybody, let's do the drill and get the QR codes out. If you were to start a new FPGA design tomorrow, which security features would you use? And then production team, do we have a bar graph we're able to throw up? Perfect. Okay, we've got a few responses coming in. It's looking promising. I guess I'm in the right room, and I'm really happy to see. Oh, there it is. I took a little bit of a risk here, so we're going to stop this. I actually made a prediction before this started, and we'll see how right I was. Did we go? I actually thought it was going to be more like that. So I'm really heartened to see that some folks in this room would use security features, and I can tell everybody when we go through in the next few slides what everybody's thinking. But what's interesting is we have a lot of people wanting to use security features, a lot less none than I thought, and what I noted is that very few responses on attestation, and I think we'll see why that is so important going into the AI era very soon. So let's quickly talk about some traditional threat vectors in the FPGA space. These threats, we typically think about these as being reserved for your most highly motivated and well-funded threat actors, and so kind of out of scope for what you might be thinking for your application. But what's really interesting is we've already seen some of these techniques been proven to be commercially viable when the right motivation is there. And so bringing those down out of sort of this really advanced threat actors into the commercial space is something that we've taken a note of. These guys, as a hardware vendor, they're a little bit uncomfortable to talk about for sure. Lots of trust is placed in our hardware, and if there are problems along these lines, they can be your worst nightmare. Nevertheless, we want to acknowledge that research takes place, and what was really interesting about this paper, not that it exists, but in order to pull it off, the researchers cited needing deep expertise, deep studies, and modeling of the device behavior, and excellent coding skills to achieve the result that they did. Moving forward, protecting your investment and your proprietary technologies is often top of mind. I think as we saw in the bar chart, a lot of you were thinking encryption. And what we see is typically it can be tough to balance that predicted cost of pulling off a successful attack with the cost of managing and implementing that protection solution over time. And notably, this isn't just a technological solution because it relies on the strength of cryptography, but it also relies on the existence and the secrecy of a key. And so you need both the technological and the social solutions to protect your the things that you want to protect over time. And then finally, we see threat actors in this space continue to evolve. Typically, they're focused on financial gain through short-term disruptions. So this seems like a more esoteric type of attack against FPGAs. Nevertheless, trends are instructive. And so if you're not employing your security features and you're leaving a hole open, somebody's there looking for it. And I think if you or your customers consider your hardware, or particularly the data that flows through your hardware, to be critical to your business, then you should act like you have critical infrastructure too. So we've talked through a couple different threat vectors and how can AI possibly affect all of them. Well, the theme today, right? It's going to accelerate those threat actors on every level. And it's not just me saying this. The UK National Cybersecurity Center has already quoted the expectation that AI will increase both the volume and the impact of attacks over the next couple of years. So this time frame is immediate. The United States DHS is also citing risks, particularly to critical infrastructure, specifically related to AI. And then, again, notice this headline that came out on the Monday following that tech outage that everybody knows about that happened this past summer. That happened on a Friday. So this headline was Monday. And that outage had nothing to do with a security vulnerability. It was a failed software update. And what were, the problems, who was capitalizing? They were folks trying to come in and say, hey, your line's down, let me step in, give me some money, I'll get you operating again. They weren't representatives from either company involved. They were just trying to make a quick buck, and they were very successful at it. So we really have to take note of it being both a technological problem and a social problem. And how can you respond in this type of environment? So what can AI do for threat actors? And let's look at these AI killer apps and see if anything looks familiar. From here, pattern recognition, chatting with documents, decoding, these should all be quite evident that it meshes very nicely with the threat activities that take place and how they will dramatically reduce the cost and the effort, not only to come up with novel attacks, but once you've figured one out, to expand the scope of what you can affect. And then what's really interesting here is that training. The training aspect of AI is the accelerator, that feedback loop that enables the threat actors, once they've learned something, so has the AI, you can build on that. And so it really makes them, the farther away they get from you, the faster they're going. And what that means is the risks of inaction, of not using security features, or not using them properly, are not just growing, but they're compounding. So we think securing every FPGA in the face of AI and accelerated threat actors is an imperative, not only for your business, but for your customers. And in many places, it's becoming regulatory requirements as well. So where do you begin? What's most important? How do you build up defenses that are going to stand up to AI? Well, first, we should just get started, and get started soon. Use the features that are built into your FPGAs, and establish some baseline, for example, authentication, that raises the cost for threat actors to pull off a successful attack. But in some cases, we can go much further. What you really want to start doing is thinking about building a cohesive response plan. And I don't just mean words on paper. Have a technological solution that satisfies 3 key metrics that your customers are going to want to see: speed, authority, and trust. So I said that threats are going to be social as well as technical. So how is your customer going to get to you, and only you, for help when lines are down? How can they know that the updates that you need, or that they need to get back online, are coming from you and only you? So plans that you can give to your customers that are backed by technological solutions are value add and a strategic advantage for your devices. And the best of all worlds is to use trusted hardware to build a responsive solution. And when you have trusted hardware, that gives you 2 of the 3 key metrics. It allows you to speak with authority and allows customers to build their trust in your solutions. And because you're standing on trusted hardware, you can also employ constant monitoring, and that gives you the speed of response that your customers will be looking for. And with that constant monitoring, any data that you're generating can then also be used to get AI on your side and use it for defense. And I bet you can't guess where I will say to go for these kinds of solutions. Oh no, what's happened? Oh my goodness, let me see if I can fix this. We get it? Okay. I don't mean them, I mean us. And that's what it is. It's the ability to recover quickly. And yes, Altera FPGAs have the security solutions to meet this pressing need. And it begins with our extensive efforts to build in recovery into nearly every aspect of our security solutions, starting with our secure device manager and its firmware-based architecture, and the ability to replace keys as you need to when you're responding to a security event. Now, given hardware that you can establish and maintain trust in over time, we also have the ability to build up certificate chains from the hardware all the way through to your currently running design. And finally, once this is combined with the flexibility of FPGA, you have all the ingredients you need to meet the pressing needs of security in both AI and the quantum era. So here's a quick look at our secure device manager that provides our configuration and security. It's very much what you would expect from a small secure element subsystem. We've got redundant processors, some hardened cryptography, and protected key storage. We've got a ton of advanced security capabilities that we build on this hardware. And we're really proud that this is a core Altera technology, and we built it not only into Agilex 7, but 5 and Agilex 3 as well. So we're really proud to bring this to both the mid-range and the low end, and have the features come across our entire product portfolio. So let's dive into a specific feature that enables you to build this cohesive response on top of trusted hardware. And as you can see, that's attestation. So how does this work? Well, you have Quartus, and you have your FPGA. And Quartus obviously outputs a bit stream, and you can tell Quartus how to output some artifacts that tell the FPGA who you are, why you're its owner, and the security settings you want to apply. Both of those get applied to the FPGA. And now you have a single secure FPGA at one point in time. Now, because this is an FPGA, I bet you have a server that's going to provide updates to your designs over time. And it's likely that this, or unlikely that this is synchronous across all of your devices in your deployment. So how does your update server know which of your FPGAs got your updates? Better yet, how does your server or your network know which FPGAs are your FPGAs? So wouldn't it be nice if Quartus output a checklist of the things with cryptographic identifiers of your designs? And wouldn't it be great if the device output a certificate that said, this is the device's identity and this is the design that it's running? And wouldn't it be great if both of those could go over to your server and you could have confidence in the state of your deployed devices? Well, this is the essence of attestation. So we'll dig into how we built this feature and show you how, from this feature, you can build a rapid and authoritative response solution. So it all begins with a unique device secret. This is generated on device when we build the part. So only our SDM has knowledge of the UDS. This isn't some value that we're creating and programming onto the chip. It's generated on the chip. From that UDS, we use a key derivation function to generate a device identity key. Now, these are all asymmetric keys, so the device holds the private keys, and then we gather the public key from the device. We log that device identity public key during manufacturing and hold on to that idea for a minute. When the device starts up, a lot of things start happening. We load in the firmware that powers the SDM's features. We hash it to measure the firmware that's loaded, and we plug that hash into two places. One, a key derivation function to get a firmware key, and two, a signature algorithm from the device identity key. And now we have a certificate over the firmware key and the device identity key. So now you have a trust chain from the hardware to which firmware the SDM is loading. Now repeat that process as the bit stream is loaded. We'll take measurements of the bit stream, do the key derivation and signing processes one more time. And now you have a trust chain extending from the hardware through to your running bit stream. But there's one last crucial piece, and that is the ability for your server to send a challenge or a token to the device. And that token is a one-time value, and it's what we do is we use the alias key to sign that token, and this gives you real-time proof of liveness, that you're not just getting somebody on the other side of the network that's handing you back these certificates that they've seen before. It's a live value that's come back. So you really have that real-time confidence in the state of all of your devices. Now, I said your devices, but this hinges on you trusting that device identity key. So when a device hands you its identity key, how do you gain trust in it? How do you know that this is a key that came from a device and not just somebody randomly on the other side of the network? Well, we have a web service called IPCS, where I mentioned we logged all of our device identity public keys. We sign them and make those certificates available on that web service. So this allows you to gain trust that a public key comes from an Altera FPGA. And you can record the certificates that you get at the initial device enrollment. You can also take it one step further and create your own certificate chain over your device identity keys. And since nobody else can generate this certificate chain, you can have all the confidence you need to say that the devices that match these certificates are your FPGAs. So putting this all together again, you have your device, which has its bit stream and security settings, and your servers, which have a list of expected FPGAs and expected states. The FPGAs are outputting their signed certificates. They get sent to the servers, which then verify the results. And this can happen automatically every time you issue an update, forming this continuous feedback loop that allows you to feed this real-time monitoring data, perhaps into an AI for intelligence defense. Now let's see how that would work when we're talking about multiple devices. So again, we'll start with a server. This time we'll consider multiple devices connecting to it. First is a device that missed its last update. Well, it's going to emit a certificate for the old design, which your server will immediately notice and give you indication that this device still needs to apply an update. Now consider a device that picked up the latest design but missed the update to its security settings. Well, this is evident in the certificates as well, and your server will detect and allow you to act upon. Now let's consider a true attack, an FPGA that's not running your design and not running your security settings. Well, because this is all powered by the SDM, and the SDM holds all the private keys, the only certificate that the device can generate are ones that match the state of the device. And your server's absolutely going to pick up on this and probably block the device from your network. All the while, your devices that are behaving normally continue to connect and operate at full speed. And so this is why we call it intelligent defense. So to recap, securing your FPGAs, we think, is your imperative. And you should get started as soon as possible, even with the baseline features. But in the AI era, you really should consider having a rapid response plan that allows you to establish authority and your customers to build trust in your solutions. And the best way to do that is to use the attestation features in Agilex devices. So one more time, a proactive defense based on trusted hardware is achievable today, and we think it'll help you stay ahead of AI-accelerated threat actors. And because that's not enough, quantum computing also threatens to upend security as we know it. And so let's take a look at why FPGAs are, we think, ideally suited to help you manage the transition to quantum cryptography and why you want to get started now. So the US National Security Agency has established a timeline to transition various technologies to post-quantum algorithms. And if you take a close look, and I know it might be hard to see in the room, 2024 is here. So the vast majority of these start either next year or the year after. And you might be wondering, well, quantum computing isn't happening immediately. So why do I need to get started so soon? Well, Mosca's theorem provides a clue. And Mosca's theorem states that if it takes you some time to transition to post-quantum cryptography, and you define some long time where your data needs to be protected, and then if the time it takes for a cryptographically relevant quantum computer, one that's capable of executing the algorithms and having all of the qubits together needed to attack the pre-quantum algorithms, the time that it takes for one to become available is less than the sum of the previous two times, then the data you wanted to be protected can be at risk. And so here's the first reason why FPGAs are the ideal post-quantum platform. If you can start your transition to PQC faster because you're on FPGAs, and you still have the same data protection requirements, and we don't know, so you can't control how long it'll be until a cryptographically relevant quantum computer will become available, then the best thing you can do to reduce risk is to reduce the time of your transition. So obviously, we think the best solution available to do so is FPGA. You can start that transition now. And let's do a deeper dive onto what exactly is the threat. Why start using quantum cryptography or quantum safe cryptography today? So here we have Alice and Bob, and they want to communicate securely. So they do what any self-respecting stick figure will do. They'll initiate a key exchange algorithm over the internet. The key exchange algorithm will allow them to independently arrive at a shared secret that is not transmitted over the internet. from that shared secret, they can also derive an encryption key. And then Alice will take her document, encrypt it using that key, and she can send it over the internet, which Bob receives and decrypts. And now they're both happy they communicated over the internet using a quantum safe algorithm. What's that? AES is quantum safe. So they should be good, right? Well, let's introduce Eve. Eve doesn't like Alice or Bob, and they don't really like her either. Nevertheless, Eve has access to the same internet, and she's been listening. So now she has copies of the things that were transmitted over the internet, that key exchange and the encrypted document. She can't do anything with them today, but in the future, she gets a quantum computer. And now she can cause trouble because the key exchange algorithm itself is vulnerable to a quantum computer. So with that, Eve takes the key exchange data and her quantum computer outputs the shared secret. Once she has that, there's nothing Alice or Bob could have done in this step deriving any keys from the shared secret that would prevent Eve from then gaining the encryption key. Once she has the encryption key, she takes the encrypted data, decrypts it, and now she has the document. And Alice and Bob are very unhappy. So the post-quantum algorithms that would have helped Alice and Bob are very new in cryptographic terms. And what we see already are leading cryptography researchers believing that it's likely that these new algorithms that have yet to stand the test of time will themselves need to be updated. And so the ability to update your algorithms quickly and in environments where algorithms have the potential to change are hallmark applications for FPGAs. And maintaining continuous data protection is absolutely achievable using FPGAs to maintain that flexibility. And we're very happy to have our partner, Cyphera, and I'd like to introduce Tommy to show you exactly how you can start transitioning to post-quantum cryptography on your FPGAs today. Tommy?
And thank you, Altera, for having us today. It's been a great day so far. So my name is Tommy Lampila. I work for Cyphera, which is a company based out of Finland. We're apparently up north. We're having first snow today, so I do appreciate being here today. Cyphera focuses on implementing cryptographic algorithms and protocols directly on hardware and licensing them in the form of IP cores to device manufacturers and our partners and customers. So I think, Tony, you explained really well the reasons that we're seeing our customers implementing post-quantum cryptography already today. On one hand, you have the data that you need to secure and keep confidential, maybe for the next 10 years, 20 years, or throughout the course of our lifetimes. And on the other hand, you have the devices that we're designing today that need to be out in the field, operational and secure for the next 10 years, or in some cases, more longer. So luckily, NIST has got us covered. U.S. National Institute of Standards and Technologies announced or released and finalized their standard for post-quantum cryptography in the form of 3 algorithms. One for key exchange to protect against the scenario that Tony explained, ML-Chem, and 2 for digital signatures, ML-DSA and SLH-DSA. We've already, at Cyphera, we've already implemented 2 of those, ML-Chem for key encapsulation, key exchange, and ML-DSA for digital signatures. Like Tony mentioned, the standard is really new. The final standard was published last month. And in cryptography, new isn't always the best. We kind of like things that have been around for a while. And even though these algorithms have been subjected to large amounts of scrutiny analysis by the global cryptographic community, there's still a chance that a weakness will be found in one of them late in the game. So what government agencies and security researchers are recommending is the use of hybrid cryptography for a time being or for a time window of, for example, up to 2030, which is a recommendation by ANSI in France. So this will give you the security net of having both technologies, being protected by both technologies. So if traditional cryptography is broken by, or when traditional cryptography is broken by quantum computers, you have the PQC algorithm to fall back on. Or if one of the relatively new PQC algorithms is broken, you still have the traditional crypto to rely on. So in practice, in terms of key exchange, you basically take the outputs of the traditional ECC chem algorithm and the PQC key encapsulation mechanism algorithm, and feed them to a key derivation function, and you have your key. In the case of digital signatures, you sign the data with both a PQC algorithm and a traditional algorithm, and then verify both signatures. And if one of those fails, you don't trust the data. And this is where FPGAs are a great platform for implementing these new security technologies. If you need to update the implementation, or if an algorithm is found to have a weakness and is deprecated, you have to replace it with a backup algorithm, you can update your design, which is what we call crypto agility, the ability to update your crypto implementation. So what do these implementations look like in practice on an FPGA? They are more complex as algorithms than traditional asymmetric algorithms. They take up some more space on the device, not dramatically so. So, for example, in the case of MLDSA, it's about 12K ALMs, 70 memory blocks, and 1 DSP. And as far as the algorithms go, they are pretty much just as fast to execute, or in some cases even faster than traditional algorithms. And I'll be demonstrating both MLChem and MLDSA at the Customer Experience Center today on an Agilex 7. I'll be there for any discussions, questions that you may have. And yeah, I hope to see you there. And with that, I'll hand over back to Tony. Thank you.
Thank you so much, Tommy. Really happy to have Tommy and Zafira here. These guys are the experts. I'm sure he's forgotten more than I will ever know. So thank you again, Tommy, for coming on. So today's call to action, again, having a rapid authoritative recovery plan is essential in an AI accelerated threat era. Agilex security and attestation solutions enable you to build that unprecedented trust and recovery architecture today. So the call to action, stay up to date on our security features. We've got a documentation overview in the top link there. Stay up to date on post-quantum cryptography, and for your long-term data protection, come talk to us and Zafira. And then my email is down there in that bottom link, so feel free to reach out. And with that, I'd like to say thanks.
Altera, accelerating innovators.